I'll start with the title slide here and the picture. You can see myself and Genoveva Martí, the co-authors of the work I'm presenting here, which came out last year in EJPS. And you also see Stathis Psilos, our good friend, who I haven't seen in person in a long time. And as you can see, there's a little distance between us, but maybe it's not too dramatic. He's a defender of scientific realism, and I will be defending a slightly different way of approaching scientific realism today, and criticizing at some point some views that Stathis has advocated about reference. Here I have the abstract of the talk, which you all probably saw on the announcement. I won't go through that, but if we need to refer back to it, we can. So the plan of the talk is, in the first part, I will introduce a kind of scientific realism, abbreviated TSR, that I'm defending these days. Then we'll move on to look at the main topic of the talk today, which is what to say about the traditional threat to being a scientific realist that comes from certain views that many philosophers have had about reference, and especially how reference to natural kind terms for unobservable entities, especially like viruses and electrons and protons and things like that, how reference works. So I'll briefly go over the threat that comes from being a Quinian or Kuhnian type holist about meaning. Spend a little more time on classical descriptivism as an account of reference, and then we'll look briefly at the causal historical view that was put forward by Kripke, Putnam, and others in the 1970s, which seems to not have the problems of descriptivism. But there is apparently a problem that many philosophers have identified for the causal historical view, connected with things like phlogiston. And for that reason, some philosophers of science, Stathis Psilos prominent among them, have introduced something that they call causal descriptivism, which is meant to combine the best features of the Kripke-Putnam approach to reference and descriptivism. After criticizing that view, then I'll turn to the way that Genoveva Martí and I think about the causal historical view and how it connects with the form of realism that, that I'll be telling you about in a very synergistic way to, we think, resolve these issues about reference and realism. Okay, so my view about realism comes out of lessons that I learned over decades as a philosopher of science. And one lesson is that it's very hard to be a scientific realist if you try to include contemporary physics in the domain of the parts of science that we're supposed to believe are giving us the truth about the world. And I'm speaking specifically about fundamental physics theories, which are highly problematic for reasons we all know. There's the unresolved measurement problem in quantum mechanics. We have multiple empirically equivalent versions of quantum theories, whether it's ordinary quantum mechanics or quantum field theories. There's not even at the moment a consensus among physicists about whether we should say that particles exist or just fields, or somehow both. And general relativity is not yet consistent with the quantum view of the world. Even if you take one version of quantum mechanics that you like and try to defend it as the truth, what do you say about gravity? Then is still a wide open problem. So there's all sorts of reasons to be not taking a realist attitude to contemporary physics, at least not yet. And of course, most philosophers of physics and even a lot of physicists expect that there will be future major revolutions that occur and really change, perhaps dramatically, our picture of the physical world. A second lesson that sunk in over the decades is that philosophers of science don't do very well trying to defend scientific realism when they insist on reaching into the past and trying to identify what people like Newton and Laplace and Priestley and others had in terms of truth that they were grasping about the world. They do this because they want scientific realism to have some sort of, be linked to some sort of doctrine about the cumulative progress that we've made over the centuries in science. And I think that just causes big trouble. As Loudon and others pointed out, in the history of early atomic theories and phlogiston theory and ether theory and so forth, we see that you can get predictive success, or at least some of the time, at a very early stage, when no realist stance is warranted about the theories that we're talking about. My own view about scientific method is that it may be guaranteed to lead us to the truth if nature is kind, but not necessarily quickly. And indeed, in the history of science, it has not led us quickly to the truth about anything, and especially about physics, of course. Okay, so now I'm stuck. So what I came to realize is that the early 20th century marked a kind of an epistemic dividing line in the history of science. And starting in the first half of the 20th century and then accelerating as the decades wore on, the number of epistemic handles that we have on facts in the world and entities in the world multiplied rapidly. And in various ways, the pieces of the different sciences started to fall together nicely. And we got successful integration and interdependence of different branches of science: biology with chemistry, chemistry with physics, thermodynamics with particle physics, and so forth. And I want to mention a third lesson that I learned over the decades, I think. Von Frossen tried to teach this to me in the 80s, and eventually I took the lesson, which is that inference to the best explanation is not the right way to defend scientific realism. I think that the anti-realists are just right in saying that inference to the best explanation is a terrible inference rule. It can lead you astray if you happen to have only a bad lot of explanations, which was the case in previous centuries. Or if you just have poor taste when you assess what the best explanation is. And so we should just leave inference to the best explanation out of our defense of scientific realism because we don't need it. Now, the fourth lesson is that you keep coming back to feeling like a scientific realist, no matter how many books you read, written by social constructivists and Hasek Chang and others. You get into this anti-realist mood, and then you go back to your regular life and you turn on the television and fire up your cell phone and go to the doctor and so forth, and you just can't hang on to that anti-realist attitude that you had. And that's because there's some areas of science where serious doubting has just become crazy. So think about certain areas of geology, biology, chemistry, and so forth. We've discovered a lot of facts in these fields, and they're typically known by multiple routes. We don't just have one piece of evidence or one route of evidence for getting at and confirming these facts. We have many. And the branches of our knowledge are interconnected in various complex ways, which Quine talked about as a web of belief. And this means that we have multiple epistemic handles, is the term I like to use, on most of the core contents of these areas of science. And the interdependence and interconnectedness of the sciences entails that if we were to suppose some core parts of these fields seriously wrong, radically wrong in the way that phlogiston theory was wrong, that requires supposing a chain reaction of further beliefs being jettisoned and replaced that would have essentially spread through the whole of our scientific lore. And so the key way I think that one has to defend scientific realism is to point out that the only real worked out consistent hypothetical scenario that we can come up with that would make sense of these core parts of our science being really wrong turn out to be just radical skeptical scenarios, like Descartes' evil demon or Putnam's brain in a vat story, the Matrix, what have you. And then the point is, maybe epistemologists have to worry about that, but that's not our job as philosophers of science. That kind of radical epistemological skepticism is not on our plate. So if that's what you have to appeal to in order to raise doubts about science, realism has won. And so I dubbed the new form of realism I want to defend tautological scientific realism, because it says we have good reason to believe in the truth of the current parts of science, which are such that we cannot imagine a scenario in which they're seriously false, unless that's via some radical skeptic scenario. Now this way of thinking about realism, I say, captures the core of the intuition that Putnam was relying on when he gave his no miracles argument. You know, many philosophers have said, no, the no miracles argument is one way of talking about inference to the best explanation. I don't think so at all. The no miracles intuition is that there's no way that all this stuff, which is so interconnected and so highly confirmed, could be completely wrong. So that's the way I think about it. All right, so just to highlight a couple of pieces of this kind of doctrine of scientific realism, we have good reason to believe in the truth of parts of current science, which are such that we cannot imagine in a scenario where they're seriously false. So this is a restricted realism in various ways. It's selective because we exclude fundamental physics and pre-20th century science pretty much entirely, unless it's some bit that has survived intact because it's basically common sense. The quasi-tautological character of this doctrine, if you see it, I say is a virtue and not something to be ashamed of. But the statements about what we're supposed to believe are the true bits of contemporary science would have to be very carefully formulated. You'd want to allow for the usual thing that realists say, which is we're supposed to believe in approximate truth because there could be minor issues with our current lore. But that's not a problem. Or if you think it is, we can talk about that in discussion. So what are we supposed to believe science has already given us as truth? Well, basically what common sense and scientists tell us at this point can't be wrong. Again, when expressed appropriately. And this will include some bits that we would identify as physics, but I would call it something more like high school physics and the associated ontology. So for example, there are things or phenomena in nature that correspond closely, if not exactly, to the intro physics description of electrons. We know their main properties and behaviors well, and we produce them and manipulate them skillfully and reliably. So while we may change some elements of that description in the future, we will never decide at this point that it's best to say electrons don't exist. After all, they never existed. Another favorite example of mine, there are invisibly small infectious agents that replicate inside living cells of other organisms, are much smaller than any bacteria, et cetera, et cetera. Talking about viruses, of course, which we're all tired of. So we're supposed to believe parts of the contents of our most successful theories, and including some postulations of unobservable entities, or at least not observable directly by human senses. Always, these things should be suitably, carefully worded. Now, I mentioned before that we have epistemic handles, lots of epistemic handles. Those are modes of epistemic access, things that we believe give us information about some aspect of the world or allow us to manipulate the world in some way or perceive it or even refer to it and so forth. I don't have a tidy definition to give, but I hope that the idea and the name handles is suggestive. One sort of handle is the theoretical roles that may be played by some entity or kind or something like that, where those roles mesh with other things, other bits of knowledge that we take to be solid. Observable phenomena or effects that are attributed directly or near directly to a theoretical posit are further epistemic handles. Experiments and observations allowing us to narrow down the possible properties of some item, those are other kinds of epistemic handles. Microscopes, of course, are one big type of epistemic handle that we have on very small things. Linguistic handles, kind terms that we introduce by reference fixing, but almost never only by description. And we'll talk more about description and reference later. Another kind of epistemic handle is using a thing or a claim as an essential tool or premise to discover further things, because this is the kind of thing that ramifies the entanglement of our theoretical lore and makes much harder any postulation of a skeptical scenario that doubts a core area of science. Okay, so I'm just giving you examples of what I mean by epistemic handles. Now let's turn to talking about reference and unobservable theoretical kinds, like electrons, neutrinos, viruses, and so forth. A proper understanding of how reference to natural kinds works is helpful so that we could see clearly how reference can be stable across changes in theoretical beliefs that can sometimes be quite important. We have had changes in belief about things like viruses and electrons and magnetic fields and so forth, at least within my lifetime and many of yours. And we want to see clearly why it's correct to say that certain entities are here to stay, that even if we change some theoretical beliefs, we're not going to ever have to say, the thing we thought we were talking about just never existed. So if we have this understanding of reference and how it works, that can reinforce the claim that things like HIV, the human immunodeficiency virus, and electrons are never going to go the way of phlogiston, which has just been jettisoned from our ontology. So the first threat that comes from reference considerations that I wanted to talk about, I mentioned, is connected with taking a holist attitude towards meaning. There's this Kuhnian, Quinean picture of meaning as holistic. The meaning of a term like electron or mass is in part determined by the whole web of beliefs that the community has at a given time, or in Kuhn's terms, the paradigm reigning in the relevant scientific community using the term. This view entails that when a very significant change occurs, or very significant changes occur in our overall beliefs, then it seems you have to conclude that the same term orthographically, like mass, before and after those huge changes, before and after the revolution, don't mean the same thing, which may make you think that scientists living in these different paradigms, pre and post-revolution, are not even talking about the same things. And this has been one of the famous worries challenging a scientific realist perspective. Here's how Putnam expressed the concern back in 1978. Let us suppose that they are right and that electron in Bohr's theory does not refer to what we now call electrons. Then it doesn't refer to anything we recognize in present theory. And moreover, it doesn't refer to anything from the standpoint of present theory. Speaking from that standpoint, the only things Bohr could have been referring to were electrons. And if he wasn't referring to electrons, he wasn't referring to anything. So if we use present theory to answer the question, was Bohr referring when he used the term electron? The answer has to be no, according to Kuhn and Feyerabend. Okay. This worry is not just about whether Thomson and others were referring, or Bohr, but also it obviously extends to us today. We expect major theory changes to keep happening in science, especially in physics, where, as I mentioned, we're expecting future revolutions to happen. So it's reasonable to worry that future physicists may look back on our uses of electron or photon, and if they have this Kuhnian perspective, they may judge that our talk of electrons was just empty, not referring to anything after all. And since those future physicists will be in a much better epistemic situation than us, the worry is that our assertions about electrons today are just empty prattle, which is to say, anti-realists are right. So we don't want that. Now, let me move on to the second threat, because it's really goes hand in hand with this Kuhnian threat. The danger was that because the beliefs associated with our theory may change in some important ways, the conclusion follows that you weren't referring to anything in the past after all, if you're referring to something now. And this obviously makes the descriptive content that we associate with theoretical terms decisive for the question of whether they refer or not. So now I'm going to just talk more generally about descriptivism as an approach to meaning and reference. Let's see, there we go. So the descriptivist thinks that the meaning of a natural kind term or property term, say electron or mass, is typically given by a set of descriptions that are supposedly true of the denoted objects or property, and jointly should pick out a unique referent in the world. So if the term denotes anything in the world at all, it denotes whatever kind, entity, or property is uniquely picked out by virtue of satisfying those associated descriptions. That's the basic idea. There's a variant of descriptivism that is sometimes still proposed by philosophers of science. Cluster descriptivism sort of relaxes the basic idea and says, well, there's a set of descriptions which may form a kind of a cluster possessed overall by the linguistic community, not necessarily any one speaker. And reference is determined by satisfaction of some importance-weighted majority or core of the descriptions in the cluster. So some descriptive elements may be incorrect without this meaning that there's no referent. And that the idea is that that should diffuse the worry about referring to nothing because you have some incorrect description in your set of beliefs. Here's how Chakravarti expressed the threat posed by descriptivism in general in a much more recent work. Even in cases where successive theories ostensibly refer to the same kind of object, changes in how it is described are sometimes so great that it may not seem entirely credible to maintain that each of these theories takes the same object as its subject matter. How can a realist speak of knowing an object, O, if it turns out that the sciences were and may well now be mistaken in their descriptions of O? Is it reasonable to assert that O exists and yet be open to the possibility that one's conception of O in terms of the sets of properties a theory associates with it may change, perhaps greatly? And so on. So I think you see the threat that we're interested in diffusing. Now, the good news is that as a theory of language, of meaning and reference, descriptivism is wrong, at least for most names and natural kinds. We don't want to say that it's always the incorrect account of how all expressions work. It may be that there are kinds of expressions or individual expressions in language that basically function the way descriptivists say. But overall, it's not the right view about meaning, and this has been widely adopted as a viewpoint since the arguments of Kripke and Putnam in the 70s. One type of argument that was prominent are called ignorance arguments, which is the simple fact when it comes to, say, names for people, speakers can refer to a person, or a natural kind for that matter, without knowing any description that is sufficient to determine a unique referent. Kripke's nice example was that many people can talk about the physicist Feynman, but they don't have any description in their head that would single out Feynman and distinguish him from Gell-Mann. Say, a famous physicist that works at Caltech, that wasn't enough back in the 1970s. There are also error arguments, which is that it's just ubiquitous that speakers may associate incorrect descriptions with a name or a kind term, and yet intuitively they still are able to refer to the person or kind that we all think they do. That may be the description that many people have in their heads. And his famous Gödel story, where Gödel didn't actually prove the incompleteness or any of that stuff and was a thief who took it from someone else. So these kind of arguments put great intuitive pressure on descriptivism. Kripke's basic examples focus on what one speaker has in their head, and it's more common later on to just take the descriptions out of an individual speaker's head and put it into the linguistic community, but that doesn't fully solve the problems because an entire linguistic community may be confused or, without knowing it, not have enough descriptive information to pick out one kind from another, one person from another, and so forth. So it doesn't fully solve these problems. And as I mentioned, the upshot for large swaths of philosophers of language, at least, was to move in the direction of what's called the causal historical picture of reference, or direct reference theory, it's often called also, which was first articulated by Kripke and Putnam and others in the 70s. Let me go back to seeing the problems for descriptivism, though, with respect to a couple of natural kind stories, natural kind terms that may help you to see why descriptivism has problems in the scientific realm, and even when we look at the whole community. And this is an example that Genoveva and I came up with, well, we thought that there might be an example because of things we heard about the dinosaur Triceratops, I think. And then in looking into it, it didn't quite fit what we wanted, but we stumbled on this kind of dinosaur called Megalosaurus, which is a big boned dinosaur. And when the term was introduced as the species associated with certain finds, fossil finds, the cluster of important characteristics ascribed to this dinosaur by early researchers would have included things like this: amphibious, quadrupedal, and up to 22 meters long. But later decades of research revealed that megalosaurs were land animals. They walked upright on hind legs, and they grew to only 6 meters or so in length. So if you look at the change in description is dramatic. And for descriptivism, even if it's a cluster descriptivism, it seems hard to avoid the conclusion that if we're now referring to a species with our use of the word megalosaur, we're not referring to the same thing that they were back then, or they were not referring to anything at all, most likely. But that doesn't seem intuitively right. Okay, so I've talked about that. Let me see. Okay, electron is another example that philosophers talk about all the time in connection with realism. And it's a good example for our purposes because the early people who investigated electrons had some correct beliefs about them and some incorrect beliefs about them. So Thomson, who won the Nobel Prize for the electron, and most of his compatriots believed that electrons compose cathode rays, have certain constant mass and constant negative charge, the values of which were not yet known, and contribute to making up atoms. Although it's worth pointing out that in the early days of investigation of electrons, not all physicists thought that they were part of ordinary matter. But so far so good. We've got a few descriptive things associated to the word electron, which we still believe are true, but we could start asking further questions. So you might go back in time and ask Thomson, Do electrons have definite positions at all moments of time, and do they follow continuous trajectories through space? To which the answer would have been yes, of course. Whereas a contemporary physicist would say definitely not. Well, unless he or she were a Bohmian. You might go on and ask Thomson, does an electron have a wave-like nature? Does it have intrinsic angular momentum? Might it have further internal structure or subcomponents? And the answers would probably be no, no, maybe, but I doubt it. But a contemporary physicist would answer these questions, yes, yes, almost certainly not. So there's a lot of discrepancy, as we see, between very important core properties that we ascribe to electrons today compared to things that would have been ascribed by Thomson and others. So at least for the Kuhnian, it's very clear that referential continuity is not going to be very plausible to maintain. And you could argue that also for descriptivists, it's going to be hard to argue that when we talk about electrons, we're talking about the same things that Thomson was and for which he was credited and given a Nobel Prize. But it could have been even worse. Imagine, just fictionalize the history, the early history of the electron slightly, and imagine that Thomson and other physicists had believed that the mass and charge of electrons are variable rather than a fixed constant value. And suppose that it had actually been a consensus rather than a minority opinion for some years that electrons are not components of atoms and matter. Then the only true component description in a plausible cluster that would have been held by Thomson and the others would have been this: electrons are negatively charged particles that compose cathode rays. And now there's the problem of an error argument that looms here, because reference, you might say, either fails or is ambiguous, because cathode rays, especially back then, contained not just electrons, but also negative ions of various atoms. So the negative particles that were present in cathode rays were not just electrons. But again, it's not intuitively plausible to conclude that Thomson was talking about nothing, or that he was talking about both electrons and negative ions, or that we're not talking about the same particles that he was. And so this leads you to want to adopt the causal historical picture of reference, in which a term gets introduced and associated to a thing or a natural kind paradigmatically by a baptism event or a dubbing event in which a person or a thing or a kind is ostended and given a name. The name is attached to the thing or the kind. But there are other ways of singling out the named item that are possible. And it's important to note that even Kripke insisted that one way you could single out the thing you want to ascribe a name to is by giving a description of it, fixing reference by a description. And that was the case with the introduction of Neptune to refer to a hypothetical planet beyond Uranus. In the causal historical picture, the term or name is then passed from user to user in the linguistic community, making a kind of a causal chain of usages of the term that lead back to the initial introduction. And this is where the causal gets into the causal historical picture. And the idea of this approach is that reference is preserved in later uses, no matter what descriptive information the later users may associate to the term. Maybe later users of the term become confused. Maybe they don't know enough to single out a single person or a thing. That doesn't matter. The reference is borrowed from the initial successful cases of reference. And this has led to the charge that we have a third threat here, which is that it's too easy to get success. Referential success on this picture is just too easy. And unobservable natural kind terms may be introduced by a combination of description and ostension, pointing to some phenomenon. So for example, call the fundamental neutral particle which made these tracks, where I point at some picture from a cloud chamber photo, T. Doesn't sound like a bad way to set up the name. But the worry has been for some philosophers that, well, we might think of what happened with phlogiston this way. Priestley says, call whatever substance is principally involved in combustion phenomena such as these, phlogiston. And then the alleged threat is that phlogiston, we want it to not refer to anything, since we think it doesn't exist, but maybe it has all along referred to oxygen. If you're not a descriptivist and you believe in this direct reference story, the worry is that your word may latch onto something that you don't know what it is at all. You have no idea what it's latching onto, but your word latches onto something maybe that you don't want it to latch onto. Okay, so that's been the concern raised by some philosophers of science. And they have responded by developing a hybrid account of reference that's meant to bring the two things together, a descriptive element and the Kripke type direct referential picture somehow combined. Now, the first thing to note is that causal descriptivism as a theory about reference was first introduced by Lewis in 1984, and it's completely different from what the philosophers of science talk about, especially we'll be talking about stathis psilos. So if you already know what Lewis meant by this, just forget that. But the idea, again, is a hybrid theory of reference, combining something like causal interaction with the referent found in the causal historical views account of name introduction and baptism. And secondly, reference being fixed in part by associated descriptions, which these philosophers argue seems necessary anyway for natural kind terms for unobservables, because how else are you going to be able to say anything about what you're talking about? So Psilos's causal descriptivism goes like this. Terms for unobservable kinds or theoretical entities are introduced by an overall description, specifying that the entity is the cause of a certain phenomenon we observe, or helps explain a certain phenomenon, and also satisfies certain other descriptive conditions. So two conditions must be satisfied for a theoretical term T to refer to an entity or magnitude X. First condition, X must be the cause of a phenomenon phi, intuitively the phenomenon the scientist wishes to explain with the help of T. And B, X satisfies a description D of X that captures the ways in which the posited referent is supposed to be causally connected to the phenomenon phi. And now, this may work for electrons in the way that's desired. We think that neutrino is a case that doesn't work very well with this, even this hybrid view. First of all, neutrinos were not introduced as the cause of any phenomenon phi. They were introduced as something needed to balance the books of energy conservation in quantum fusion reactions in the sun. So to say that neutrinos cause energy conservation or cause it not to be violated, we think would be an abuse of language. But there's no other known, there was not at the time any other known observable phenomena of which neutrinos were thought to be the cause, to play the role of phi in Stathis's condition A. And secondly, the idea is that there's this descriptive part D of X where descriptive content is ascribed. You say something to help single out the particle or the thing being referred to. And Stathis says that this thing may evolve over time. We can refine the descriptions that are in this descriptive part D of X. So the trouble is that neutrinos were initially thought to have either 0 or very low rest mass. People were not sure. But then theoretical developments in the 1940s and 50s seemed to show that neutrinos must have 0 rest mass. And that was a very widely held view for decades. By the late, say, 1950s, this property of having 0 mass would have been put into the core part of any plausible descriptive part, D of X, capturing the community's belief. So this looks like a potential case in which the refinement of D over time, which Stathis says we have to have, could lead to a referential failure. Because as probably most of you know, then in recent decades, we decided, oh, oops, neutrinos do have mass after all. Okay, so the point is, from our perspective, Psillos's causal descriptivism is still too descriptivist. The point is that if you tweak the theory in the right way, we think it may give intuitively right verdicts on most historical cases. But insofar as referential success remains linked to the truth of some core part of some description, one can imagine cases in which the theory declares referential failure where intuition would rather see success, as in the example of neutrino just now. And I'll give a fictional example using the Higgs boson in just a moment. So we say go back to the causal historical approach, but now integrating some of the ideas that I was telling you about of tautological scientific realism helps you refine the view in a way that makes it stronger and makes it clear that there's no threat from things like phlogiston. So in a paper in 2015, Genoveva pointed out that we shouldn't be misled by oversimplified dubbing ceremony stories, which were the typical things talked about by Kripke and others in talking about how we name people, babies usually. That's not how it has to work for referential terms in general. And in fact, what's important is the establishment of a referential practice in a community. That's what's required to incorporate a name or a natural kind term into the language and allow it to be now a thing that directly refers to something. And this establishment of a referential practice is a process. It takes time, and there can be early stages when there's no reference or there's ambiguous reference, and eventually things settle down unless they don't, as happened with phlogiston. And both of us realized when we were working on this paper that this establishment of a referential practice occurs when the use of the term in the community becomes widespread and there are enough agreed upon epistemic handles on the referent guiding your future uses and the resolution of any doubts that may arise. Like the doubt, do neutrinos really have no mass? So this idea of epistemic handles actually integrates nicely with the understanding of what it takes to set up a referential practice in the community. But once the practice is up and running, continuity across theory change is guaranteed in many cases, even if we change very important beliefs about the kind, things that you would have to put in the core, intuitively speaking. Contrariwise, phlogiston is no threat to the causal historical view. The initial central description associated with its introduction, namely substance given off in combustion, never picked out anything because nothing is given off in combustion, no substance anyway. And equally, no other epistemic handles emerged that would let us say that a referential practice had stabilized around the word phlogiston. Now, you can imagine alternate histories for the early history of chemistry where a successful practice does emerge using the word phlogiston. So some philosophers have suggested maybe this idea that it's given off could have been sacrificed, and maybe then phlogiston could have turned into a name for what we call oxygen. Hasek Chang, in a 2012 book, argues that it might have happened that chemical potential energy turned out to be the referent of phlogiston. That's fine, because then phlogiston would simply have become, in those alternate worlds, a word referring to those things, which we do think exist. So that's not a threat to scientific realism at all. Okay, so in conclusion, scientific realism can be defended successfully, we think, for large parts of contemporary science, excluding fundamental physics theory, but including a lot of what we might call high school physics entities and lore, like electrons, protons, neutrons, and some of the basic properties that we ascribe to them. Descriptivism as an approach to reference to unobservable natural kind terms raises worries for scientific realism. The worry that our current theories may be mere empty talk, not actually referring to anything out there. The causal historical approach, however, to reference, properly understood, diffuses the concerns that come out of descriptivism. When a referential practice gets established and connected with sufficient epistemic handles, we can be sure that future changes of theory will not entail current referential failure. I was going to tell you about a story with the Higgs boson. If I can take just 1 minute, that will be useful. When the Higgs boson was introduced, it was described as performing a theoretical role, much in the way that neutrino did, the theoretical role of being responsible for giving mass to certain bosons, certain other particles. But we think that it's perfectly conceivable now that in the future, some future day, we might find out, theoreticians might decide, that the Higgs particle is actually not connected with the existence of mass in any other particle after all. But imagine that in this alternate scenario, this future scenario, we've been producing Higgses at CERN star, the upgraded version of CERN, for decades. We've been exploring their properties, using them to search for even higher energy particles and so forth. Then what we say is that our referential practices regarding the term Higgs boson will have probably stabilized on those particles that we're producing in CERN. And at that point, it doesn't matter if we completely change the theoretical description responsible for certain other particles having mass that was so important in the introduction. We think direct reference really is the better story, and descriptivism plays at most a role in understanding initial reference fixing, but not in what makes reference work. Because for any descriptive element we associate with a natural kind in science, you can pretty much imagine a story where we give up that descriptive thing, belief, but we don't decide that the entity doesn't exist after all.